All right, I guess we'll get started. Hopefully the volume's okay. So thank you all for coming. My name is Oliver Bates. I work in cloud infrastructure at Apple. What we're going to talk about today is cross-data center replication and consistency at scale, because big data, you know. Yeah, so before we get into the agenda, let's kind of quickly talk about what that means exactly. Cross-data center replication really means a process by which we keep two independently running Solr clusters synchronized with each other. Usually they're in different data centers for disaster recovery reasons and stuff like that. And what that means by keeping them in sync is that if an update comes into one cluster, it's propagated to the other so that you can read and sort of get the same search results from both clusters. One way to approach this is just to sort of have your clients write to many clusters at once, but then you're putting the burden of synchronization on them, or consistency, I should say. So, what happens if your customer is writing to two clusters, but it fails in one? Then it's up to them to resolve that diff. So it's nice if we can handle all that stuff in the back end and just have this kind of magic replication and failover stuff working for them. So, why do cross-data center replication? One obvious reason is disaster recovery. So, if your client is writing to, or indexing into or searching from a cluster and it goes down for whatever reason, it would be nice to have another cluster just sort of standing ready to go so you can fail over and quickly keep servicing requests and get out of that situation quickly. So obviously if search is a critical part of your service in some way, then a search outage means a service outage, and that obviously can be a bad thing. Another reason is to reduce latency. So here you want to think of a distributed service model. You can imagine if you're a company like Apple, you have like 100 million users, they're spread all over the planet, and you want to do probably back-end processing as close to the client as possible. So in that case, you want to have these Solr clusters that are sort of distributed all over the place, but obviously they have to be synchronized as well, so that if a customer moves or something like that, or if it's a shared account, you still have consistent data that way. So, and again, if indexing or search is part of processing those updates, then you need to have your Solr clusters replicated. So there may be other reasons you can pick them, but these are the two big ones for us. So some of you may know that cross-data center replication was added as a feature to Solr 6. We've actually been doing this at Apple for some time using a slightly different approach. And so what I actually want to talk to you about today is both of those approaches in parallel, because they're similar in many ways and different in others. And hopefully, at the end of this talk, you'll sort of see what those differences are and understand why one approach is better for certain use cases over the other one. So the breakdown of the talk is going to go kind of like this. We'll talk about high-level architecture, again, of both solutions. Then we'll talk about cluster consistency. Consistency means, if I write to one cluster and that gets propagated to the other one, can I be sure that I have the same view of the data in both clusters? In the face of leadership changes, update reordering in the queue, all sorts of failures that can come up that we know about in the distributed systems world. The next thing would be active-active setups. Here we really mean active-active writing. Being able to read from multiple clusters is sort of like the minimum requirement for cross-data center replication. So what we really mean here is being able to write at the same time to different clusters and still maintain a consistent index. The next step would be configuration. So how do you configure these systems to do cross-data center replication and what that means for operations? If you're running a bunch of clusters, ideally you want your ops to be pretty easy so that your SRE teams or whoever like you and don't hate you. Then the last thing is actually the most exciting thing from my perspective, which is very biased. We're going to talk about consistency check-in and repair. So let's say you've been running these two clusters for like a month. How can you be absolutely positive that they're actually in sync with each other? And this is a problem that exists in SolrCloud in general, just between replicas. At the moment, there's no real way to just say, just check these two things and tell me that they actually have the same data. And ideally, if you can detect consistency problems, if we could repair those automatically, that would be also pretty good, because finding out something's wrong and just not knowing what to do is not terribly helpful. Okay, so architecture. If we take a look at the Solr 6 architecture first, most of you are probably familiar with most of these pieces. We have two Solr clusters running in different data centers. In the Solr 6 implementation, it's important that there's a source cluster and a target cluster. It's really a unidirectional data flow, so you have sort of a leader-follower model. And the sort of typical way that updates are processed in a single cluster is they come in, they're sent to the leader of a shard. That leader will version the update, forward it to the followers. And in the cross-data center replication mode, it's also going to forward that via this CDCR machinery to the leader in the target data center. So one thing that's sort of important to notice from this is that while your two clusters would be independently operating, they're not actually isolated from each other because you need leaders to talk to each other directly. So you need to have ACLs and et cetera set up appropriately. If we zoom in a little bit more on the specific processing on a leader node in the source data center, when updates come in, they go through these update request processing chains, which is just sort of vanilla SolrCloud kind of stuff. When you're running in CDCR mode, after going through this processing, which means versioning the updates and stuff like that, you write them to the transaction log. In CDCR, the transaction log also acts as an update queue for replicating cross-DC. And so this is the synchronous part. Once you write to the transaction log, you return to your client, you say everything's good. Meanwhile, you have a separate thread running in the background, the CDCR replicator thread, which is pulling the transaction log for new updates. When it finds new updates, farms them out to the leader in the target data center, at which point they go through the same update request processing chain. And then they're written to the transaction log on that side, which again is this update log specific for CDCR. And in the target data center, there is no CDCR replicator thread running. And so you prevent the circular mirroring process like this. Okay, so the Solr plugin architecture is similar in many ways. And Solr plugin is the thing that we've been doing at Apple. And the naming will become clear at the very end of the talk. But it's a similar idea. Updates come in, they're processed by leaders in one data center, and then you want the leader to basically forward that update somehow to the leader in the other data center. One important difference here is the way that we've set it up is that you don't have to have a source and a target. You have it running in both directions, so you have a bidirectional data flow, which has some advantages. The architecture itself is actually quite a bit different, though. We stand up a bunch of extra services. So primarily, we have a queuing service running in all the data centers. So when an update comes into the leader in the data center that's receiving the write, it goes through the normal processing, and then it's put in this queuing service. And from there, a separate mirroring service moves it from the queue in data center 1 to the queue in data center 2. And then finally, another consumer will read it off that queue and submit it to the corresponding leader in that data center using SolrJ or something like that. So one slight advantage here is that your Solr clusters can actually be fully isolated from each other. So they're independent, and also they can just not even have the ability to talk node to node to avoid potential crosstalk issues. Another slight benefit is that the queuing service itself is actually very robust and distributed. So if you have DC connectivity issues and you build up a backlog, you have a little bit more scalability there, especially if you have very high update rates or something like that. The downside, obviously, is that we're running 4 extra services. So there's an operational cost to this, which is definitely non-trivial for small operations. So if we zoom in a little bit more on the processing on the leader nodes, in data center 1, updates come in and go through these update request processing chains again. But here we inject a few extra steps to achieve our cross-data center replication. The first thing we do is we add this doc-based version constraints processor. This is not something we wrote. It's already in Solr. And we'll talk about this a bit more later, but basically this is the piece that ensures consistency between the two clusters. So it protects against update reordering and that sort of thing. How it does that will be a bit more clear in a few slides. Then the next piece we add is this mirroring update processor, and this is something that we developed at Apple. And basically, this is the piece that at the end of processing the update locally, saying, okay, this is a good update, I like it, we'll put it in the queue so that it can be replicated across data center via that machinery that we just talked about with the mirroring service and the consumer. So when an update makes it to the data center 2, the target, if you will, it goes through the same exact update processing steps. We go through the doc-based version constraints processor in case any updates were reordered in the queue or the mirror or anything like that. And then we again go through this mirroring update processor, but this time we don't write it to the queue. The way we prevent that is before enqueuing updates, we just we add an extra parameter, which acts as a flag saying this is already coming from Solr, don't enqueue this again. And so we protect against those circular mirroring things that way. So now let's talk a bit about consistency, which is really obviously a very important topic. We'll look at the Solr 6 case first. And I want to look at the case where we have versioned updates, the sort of compare and swap style operation, just because if there is no version, it's a very trivial thing to understand. But basically the way this works is an update comes in, you have an ID and some fields, and then you specify a version, version underscore, let's say it's X. The regular logic is simply that Solr will say, does that version on the update match the version currently stored? If it does, I will accept the update. And when it writes it, it changes the version. It assigns a new version to the update, which is Y. And then this is what's written to the transaction log, and then this is what's replicated across data center to the target. So when the update makes it to the target data center, it has a different version from the original request, which is Y. And so here the logic has to be a little bit different on the target. And so we actually, I didn't sort of put this in the previous slide, but there's actually an extra step that's put in the update request processing chain when you're doing the Solr 6 CDCR, which is the CDCR update processor. And it's actually incredibly simple. All it does is it sets the peer sync flag to true so that the processing logic on the target is going to say, is this more recent than anything I've seen before? If yes, accept it, commit it to local index. And so you're protected that way. And now obviously, if you don't put a version on that original update, then all of this is exactly the same, except that you don't have that original check at the beginning. You just write it no matter what. And delete by ID, for example, also is assigned a version, and so you get the same protection that way. So the Solr plugin approach is a little bit different, and this is where our doc-based version constraints processor comes into play. So we don't use the internal Solr version. We use a separate version field, let's say doc version, and this is what the doc-based version constraints processor acts on. And the logic is like so. You submit a document with fields and ID, all that stuff, and some doc version X. And the logic is accept X if it's greater than anything I've seen before. So it's basically last update wins, which also means if your client is sending updates from 15 different sources, they're protected against update ordering and all that thing. If you decide to accept it, you write it locally, you assign some internal version, let's say it's Y, and you completely ignore that, and you just mirror the update as it came in, again with that doc version. And then in Data Center 2, the exact same logic applies. You say, is this newer than anything I've seen before? Yes, apply it. At this point, you assign a different version, and it doesn't matter. So a couple of things to keep in mind. One is that you have to version every single update with doc version, and these versions need to be monotonically increasing. The way that we usually achieve this in Apple use cases is we use the version assigned by the primary storage, if we're using Cassandra, for example, and then you have this guarantee of increasing versions. Something else to keep in mind is this doesn't protect, there's no versioning for deletes this way, right? And so actually what this doc-based version constraints processor does is it takes an add operation, a delete by ID, excuse me, and it converts it into an add. And then it replaces the document with a tombstone. And so you have a version, and so you can actually be protected for deletes that way. Delete by query does not work. So you just cannot do delete by query and expect guarantees like this. So basically, if you need to delete documents, you do delete by ID, and you create these tombstones, and you use delete by query to clean up tombstones exclusively. And when you do that, you need to make sure that you're not about to overwrite them. So one thing that we can't do in that previous scenario is use the compare and swap logic in Solr. So if you do need that, we have to do things a bit differently. And the way we do that is you provide both a doc version and a Solr version. And when you send your update, now we go through a different update processing chain, which is specific for these compare and swap operations. And we don't use the doc-based version constraints processor, excuse me. So an update comes in, and the logic is simply going to check the Solr internal version, and we'll do a compare and swap. If it accepts it, we'll assign some version. And then we replicate that across DC. But when we do that, we strip the version field provided on the original update, and we rely purely on the doc version to maintain consistency in the second data center relative to the first one. Right, so, yeah. Okay, active-active setups. So again, what we mean by active-active is being able to write concurrently to multiple clusters at the same time, which are kept synchronized with each other via this replication process. This isn't currently supported in the Solr 6 implementation. There's work being done from what I understand, or there is work that is to be done. So one day it should show up. This is something that we currently do support. And so the way that we do that is like follows. This is the diagram we looked at earlier, the sort of high-level architecture, where we have a Solr cluster running in 2 data centers with queuing services and mirrors and consumers and all that stuff. And basically, if we want to replicate updates from data center 2 back to data center 1, then we simply stand up the exact same machinery but going in the other direction. And so we have a blue data path going from left to right and a green data path going from right to left. Did I get those right? Yes. One thing you might notice is the queuing services now have 2 arrows coming in and out. There's sort of green and blue coming in. Obviously, it's one queuing service, but there are different logical queues within these services. So if you're running Kafka, it would be different topics, for example. And so you can keep the data paths separated that way. Something else that might be interesting is what if you want to have more than 2 clusters? What if you want to have 3, 4, n cluster replication? I changed the color scheme here to highlight the common services or the same service in the various data centers. So we have data centers 1 and 2 connected like this with our consumers and queues and mirroring services. And then we bring up a third data center with a Solr cluster and its consumer, and then a queuing service and a mirroring service. And basically, if we now want to have three-way replication, then what it means is any update that goes into data center 1, it goes into the queue, and the mirroring service now, we want it to replicate it to two places, the queue in DC2 and the queue in DC3. And likewise, an update coming into data center 2, the mirroring service there should replicate it to the queue in data center 1 and data center 3. So we just add a few arrows like this. And obviously, we do the same thing in data center 3 in case it's receiving writes, which is the mirroring service there will replicate from the queue to both data centers 1 and 2. So there's a lot of arrows, and this might be a bit confusing, but there are two things to take away from this. The first is that each Solr cluster is talking to a single queue. So if you have n-way replication, you don't have to change anything from the Solr perspective itself. There's really just one local queue for in and out traffic. And all the data multiplexing is done at the mirroring level, so you're kind of isolating that configuration in one layer, which is quite nice. Again, if you're used to using something like Kafka from a queuing perspective, there are features that lend themselves very naturally to this, which are, for example, multiple consumer groups under different topics. So if you have an outbound topic in every data center, you might have a consumer group for each data center that you're replicating to, and your mirroring service would simply read from all of those appropriately. This is more of a caveat or a warning than anything, but compare and swap operations simply cannot be distributed. This is a fact of life. You have to pick a central data store, which is going to be your caching data store, if you will. The only way to get around that would be to have your Solr cluster sort of span two data centers, but obviously that defeats the whole purpose. So if you do require cache semantics, then you need to elect one of your Solr clusters as being the central data store for this logic. And then if you have other updates that don't require this, then you can distribute them. And in many cases, it turns out that that's the case, which is quite nice. But sort of fair warning, cannot distribute compare and swap. All right, let's talk about configuration a little bit. So this is our diagram of the Solr 6 architecture that we looked at before, where we have updates coming into the leaders. They go through update processing chains. Then they're written to a transaction log, which acts as our cross-DC queue. Then we have this asynchronous replicator thread, which pulls from that queue and then copies over to the target data center, at which point the updates go through the update request processing chain, but with that special CDCR step, and then finally written to the transaction log as well. This stuff is all configured in solrconfig.xml, so it's done per collection. It's quite nice. It's simple. You don't have to do any sort of special new stuff. I would say the downside, though, in this particular case, is that your Solr configs are not the same in the two data centers because you have different pieces running on both sides. This has implications from an operational perspective. So if you imagine that you need to fail over because your primary went down, your source went down, you actually need to change the configs in your target, upload them, reload all your collections, and so you're introducing some delay. And when it's time to recover, you have to do the same thing going backwards. So we can actually do a very quick little case study and sort of see how this works. But let's say we have two clusters, SolrCloud A and B, and A would be our source normally, and B would be the target. If the client is usually writing to A, and something happens, catches on fire, burns down, whatever, you want to fail over to B. So in the Solr 6 implementation of cross-DC replication, what you need to do is reconfigure SolrCloud B as the source, which means changing the configs, uploading, reloading all your collections, and then you change your client traffic from A over to B after that. And at this point, you've recovered from disaster, so you actually back up servicing requests, and that's good. That's pretty fast. And while you're in this mode now, because A is down, the backlog will just build up in B. All your updates going in, they're just going to sort of hang around in the transaction log until A comes back online. And so this is where if you have a very high update rate, that could maybe get you into trouble just because your transaction log is writing to a file on disk on your regular Solr nodes. If you have a relatively low update rate, then it's really not an issue. When it's time to recover, the steps go like this. You want to recover SolrCloud A as the target, so I reconfigure. Then you bring it back online, let it drain the backlog from B so that it becomes synchronized with B. At this point, you block writes to both clusters, and then you swap them back, another reconfiguration, changing configs, uploading, reloading all your collections. And at this point, you can point your clients back to A and then resume writing again. So a few manual steps, not too bad, and a very short outwritage somewhere in between there. The way this looks with the Solr plugin architecture is a little bit different. So this is our architecture, again, from before. We have updates coming in, and they get processed sort of in an identical fashion on both sides. And this is all configured in solrconfig.xml as well. And the advantage here is that it's the same config in all of your data centers, so you don't need to reconfigure things. It's just kind of there, you do it once, and you're good to go. For completeness, this is really what the update request processing chain looks like when we're running the Solr plugin CDCR. And this is also where the plugin component hopefully will become clear. But we have the two pieces we've already been talking about highlighted in blue, so the doc-based version constraints processor, which does our versioning for us, and then the mirroring update processor, which writes to the queue. And the way this works is, in your solrconfig.xml, you specify a class name, which is going to be your replication handler. And so if you're writing to something like Kafka, then you load something which is a Kafka producer and knows how to write to those topics. If you're using a different queuing service, you can just provide whatever library you need, and then you just package that up into a Solr plugin.jar and stick it in your Solr class path, and you're good to go. So it's kind of nice. You don't add any new dependencies in Solr, and the whole thing is pluggable, so you can swap your replication mechanism at any time. So if we go back to our scenario of SolrCloud A going offline, then the failover is really pretty straightforward. All you have to do is redirect clients to B because the pipeline is already up and running in both directions. And then again, you're going to build up backlog on the B side, which means writing to a distributed queuing service like Kafka, let's say. And you have a bit more sort of faith, let's say, that this thing is going to be able to handle your load if you're down for like a day or 2 days, especially if you have very high volume going through there. When it's time to recover, you simply bring A back online, let it drain that backlog from the queue, and then you point your clients back to A, and you're back to normal again. And now this looks really nice, but again, there's a huge cost, which is that it's support. This works because you have all these extra services running. So for large enterprises, that might make sense. For smaller endeavors, it certainly doesn't. But there's a cost to this quick switch. Okay, back to my favorite part: consistency checking and repair. So again, this is really a question of, we have these two clusters that are replicated cross DC, and we want to know with a lot of confidence that they're actually synchronized for each other, so that if we do a failover or something, the view that a client has doesn't suddenly change. And ideally, if we can detect consistency problems, we'd like to repair them. And there are all sorts of reasons why two clusters may go out of sync, aside from replication bugs and network blips and whatever you want. There's a lot of sort of possibility for human error too. If you upload different schemas, for example, to your two data centers and you don't realize it, updates may fail on one side, succeed in the other. And you may get alerted to that, but it's not obvious necessarily how to resolve that. Or if someone doesn't notice, you need to have some consistency checking mechanism to catch that for you eventually down the line. So to understand how the repair part works, we need to look at one more little detail in the leader logic in the Solr plugin case, which is you have to do two things. An update comes in, you need to process it in your local Solr cluster, which means as the leader, you write it to disk and you send it to your followers. And then you also have to put it in the queue so that it gets replicated. And the order in which you do those two things matters. And what you want to do is submit to the queue first, actually. So when an update comes in, you submit it to the queue. If that fails, you return error to your client, and all is well. Well, they retried, but no harm done. If that succeeds, then you process it locally, which means writing it to your transaction log, farming it out to the followers. If that succeeds, you say everything's okay and everyone's happy. If that fails, though, then you're in a funny place. Basically, what it means is you have not written that update locally, but you did get it in the queue, which means it might succeed in the other data center, and you don't really know why. That could be like schemas are out of sync or something like that. But it could also be because of a min-RF thing being missing or something like that. But basically, you're at risk of inconsistency here. But the good news is that because you know it's in the queue, there is a chance to repair that inconsistency using the update, which is not lost forever. The idea being that we, as the server, have the ability to repair it. Of course, if a customer receives a fail, they can retry. But if they don't, then they may hose their cluster, and it's still on us to somehow get them back in sync. So we really want to make it foolproof from their perspective. So the challenge here is really detecting inconsistencies. And there are a few parts to this. One of them is, how do you actually come up with a diff between two clusters? Let's punt that for 2 seconds. And the second one is, if you do find a diff, how do you know that it's actually meaningful? And the idea is that you will basically always see a difference between your two things because of replication delays and all that stuff. And so just to illustrate that point, if we start off with two Solr clusters in different data centers with the same corpus, if we write to data center 1 and add a document, that'll replicate with some delay to data center 2. Meanwhile, we're updating the version of document 2 in the same data center. That replicates with some delay, and so on and so forth. So if I manage somehow to diff these two clusters at this point in time, I'd find that they're equal, and that's great. If I do it at some point in time a bit later, I would find that there's a document that exists in data center 1 that does not exist in data center 2, and I'm like, I have a diff, I don't know what to do. If I look again later, I would find yet some other diff. The version of document 2 does not match in the two data centers. It's X in 1, B in 2. What do we do about that? There actually is a way to detect these diffs that matter, things that are problems versus things that are not. And we can sort of understand that from a pretty trivial case, which is, let's say we start with one document, 1 as a version 1, then we update it to version 2, and this will propagate with some delay, and we keep doing that. We're just updating the same document over and over again. If I do a diff of the two data centers after that update makes it to data center 1 but not to data center 2, or before data center 2, then I'll find the version in data center 1 is 2, and in data center 2 it's 1. And that's a problem, obviously, but there's something I can glean from this, which is that because my versions are increasing, I know that data center 2 is behind data center 1. So what I can say is, if that update was not lost, then at some point in time later, I expect the version in DC2 to catch up. And so then my logic going forward is, I'm just going to check again in like a minute. And if I see that that diff is resolved, then I know it's OK. And then I'll keep checking. And eventually, if that does not resolve, then I can say there's a problem and move on to repair or alert or whatever. So the idea is when I do my checking again at some point later in time, I'll find that there's a new diff. The version still doesn't match. I sort of jumped the gun. But there are two things that I check at this point in time, and they're independent of each other. The first is I say, previously I had this diff, that the document version in data center 2 was behind that in data center 1. And then I check to see if that diff resolved, and it did, because the version in data center 2 is 2. And then separately, I also register that there's now a new difference, which is that the version in DC1 is 3, and the version in DC2 is 2. And so I sort of store that in memory, and I check again, and you just do it like this. And it's basically just an eventual consistency problem, which is fine. This all relies, of course, on the fact that we can actually diff large data sets. This is a non-trivial problem, but it is a well-known problem, and there's a lot of literature on it. But there are all sorts of reasons why you could have differences in replicated data sets. I listed a few, replication latency, update reordering, dropped updates, things that are actually problems. The problem, obviously, is that it's very difficult to compare those two things, especially over the network. If I have a terabyte of data, I can't just transfer it every 2 minutes to some other node so I can do a full diff. That would take forever. The generally accepted solution is data hashing. So you come up with some fingerprint for your data, and then you compare those. A sort of commonly endorsed technique, I should say, is something like a hash tree or a Merkle tree. The Amazon Dynamo paper talks about this, and Cassandra implements this as well. And the idea is that you build a tree with a sort of top-level hash for all your data. And if those don't match, then you go down and compare the next two. And then eventually you make your way down to these leaf nodes, and you say, OK, well, these are all the documents that actually don't match. So the assumption here is that of your huge data set, there won't be that much of a diff. And in the cases we're talking about here, that is a fair assumption to make. Obviously, if everything is completely different, then you're kind of hosed, because at the end of the day, you end up comparing IDs of every single document. So there is a breaking point for this approach. But generally, this is something that can work pretty well. And there's tons of literature, if you want to go read, listed some stuff there. So if we go back to our consistency checking and repair as a service, again, let's say that the diff problem is solved, then the program logic is pretty straightforward. And we sort of talked about it already, but basically in memory, you want to maintain some list of unresolved diffs that I've previously detected. And you store that however you want, and here I just sort of wrote it in plain text. But the idea is I'm expecting that the version should be greater than or equal to 2 for document with ID 1 and data center 2 by some amount of time. And that's the example we looked at before. And then the program logic really just loops and does 3 things. First is it looks in the list of unresolved diffs, and then it will just go query Solr directly and say, what's the version of this document? And if it's resolved, if that diff is resolved, take it out of the list, and then you move on. If it's not, you leave it in the list. And then you do a full diff of your 2 clusters again, and you find all the documents and IDs that don't match, and you sort of merge that diff with the existing one, because you may have overlapping diffs that you already detected. And then the last step is you go through your list of diffs, and you say, if anything's been there for too long, then I'm going to assume that it was lost or something went wrong, and now it's time to repair. And the repair process is this. We assume that it's in the queue. So let's say we keep a retention policy of like a week in the queue. That gives us a week of time where we might be able to find that update. So you go to the queue, scan the whole thing until you find an update with the version of the document that you think is missing, and then you submit it to the appropriate Solr cluster. If that succeeds, everyone's happy. If that fails, or if you don't find it in the queue, then you give up and you just make noise, and a person has to go look, and then we take it from there. So, that's the general idea anyway. So to kind of wrap things up here, basically we talked about 2 implementations of cross-data-center replication. And they had a very common architecture, in fact, which is that you have leaders sending updates to some queue somewhere, and then an asynchronous consumer, which is reading from the queue and forwarding those updates to the leaders in some other data center. The way this is achieved in Solr 6 is that the transaction log itself actually just acts as a queue, and then there's a separate thread which is running, which is polling this queue and asynchronously farming these updates out to the leader in the target data center. And the Solr plugin approach, or the Apple approach, whichever, we stand up new queuing services to have a bit more scalability there, and consumer services and stuff. And so again, the trade-off is this is something that scales better, but it has a big operational cost. And so for big enterprises, it makes sense. There are separate teams that can support your queue, for example. And for smaller endeavors, it doesn't make any sense because you're supporting now 3 times as many services as you were previously. And then the last little thing that we're talking about is this repair service that kind of sits on top. In theory, this kind of thing can also apply to the Solr 6 implementation, but this may not have been terribly obvious. But the repair service right now is really based on the fact that you're using these dock versions and not the internal Solr versions. And so the way that we've designed it doesn't readily apply to Solr 6 right now. But there's some thinking to do to see if we can mesh all that stuff together. And certainly if this consistency checking mechanism can be somehow recycled and used to check replicas within a single SolrCloud cluster, that would also be a really fantastic way to sort of, or a great direction, let's say, to move this project in. So this is I'm not trying to compare them, but sort of more highlight which use cases are better for the different implementations. And we basically said this already, but both implementations, Solr 6 and the Apple Solr plugin, they have strong consistency guarantees. You can be pretty sure that your updates will be processed in the same order in both data centers. From a scalability perspective, the Solr 6 implementation suffers a little bit from the fact that the queue is the transaction log, which is just a file on disk, and it's not sort of distributed the same way that a proper queuing service like Kafka, for example, is. So what this means really is if you have very high throughput, then you can rely on something like a very high throughput queue, like Kafka, which is definitely not going to bottleneck your update rate. And at the same time, if you have to take an outage for 2 days and you're writing like hundreds of gigabytes, then the queuing service hopefully can take that. The downside, of course, is that the barrier to entry is much higher. So if you just need cross-data center replication as a kind of starting point, then the Solr 6 implementation is totally the way to go. You just modify your configs a little bit, upload some stuff, and you just magically have cross-data center replication. No extra services, nothing to worry about like that. And again, this is a slight disadvantage to the plugin approach, which is that you have to have a whole extra set of services with their own configs, and and they're all distributed systems too, right? So they can fail. They have their own issues and whatever you want. From a failover and recovery perspective, again, it's a little bit easier with the Solr plugin, and that comes at the cost of this additional, operational overhead from day to day. And the active-active setup, they both do reads. Solr 6 is working on writes, or there is a Jira somewhere. And then meanwhile, the Solr plugin approach also works. Again, the caveat there is you can't do compare and swap operations in a distributed fashion. That's just logically impossible. So a couple of extra little things to keep in mind when doing cross-data center replication. These apply a bit more specifically to the Solr plugin approach. Again, you can read about the Solr 6 thing online, so I'm going to focus a bit more on the Apple thing. But basically, there's no way right now to synchronize the configs between your different data centers. And that's obviously a very important thing to have, because if your schemas deviate in some way, then updates may fail on one side and not on the other. And so it's actually very important that they stay in sync. And right now, we just, we require basically manual sort of assurance of this synchronization, which means making sure our clients, for example, don't accidentally upload something to one data center and not the other. And so that's a bit of a finicky process right now, but eventually, hopefully, we'll have some way around that, and that could apply also to the Solr 6 approach. From a semantics perspective, there are some things that change a little bit. When you ack an update on the original data center that's receiving a client request, then all you're saying is, I've written it locally, and I'm giving you the sort of semantic guarantees that apply to SolrCloud. But all I'm telling you about the replication is that I put it in the queue, and it will be replicated eventually, hopefully. And so if you do failover, then there's no guarantee that something that was visible is still going to be visible at that point in time, like just none. And the same applies to things like soft commits. You know, those aren't synchronized cross data center either. And so something may become visible to a searcher in DC1, then you fail over, and it's not visible for another minute, or whatever your configs say about bringing up new searchers. And then, of course, nothing is perfect, and there's always ways to lose data, even after you've acked something. And so in this particular case, if a client sends something and we ack it to them, all we've said is we wrote it locally, we put it in the queue, and you're good to go. If at that point in time, before the mirroring service can copy it to the remote data center, everything burns down, then you've lost that forever. That's a pretty dramatic scenario in a way, and you can sort of assume that that probably won't happen, but there are certain guarantees we just can't make, and this is obviously one of them. There are more, but these are some big ones. Here are some references and resources. I think I brought all these up earlier, but there are some JIRAs, and there's some good reading on the Solr 6 implementation. If you want to see more about ours, I guess you have it here. And then otherwise, more reading about the inconsistency detection in large data sets. Finally, our hiring plug. If you're passionate about Solr and clouds and all that stuff, we'd love to hear from you. And that's it. Thank you.